we've already seen what fully developed flow looks like for Couette flow, and that's flow between two plates. But it isn't the same as fully developed Poiseuille flow. Now what Poiseuille flow is flow that's driven by pressure or gravity. So we need to develop the velocity profile for that. So when we're looking at Poiseuille flow, the pipe is driven by pressure only. So let us start with the pipe. And so here's my pipe. And I have flow coming into my pipe. Here's my pipe center line. Everything's along the x direction. We have some radius r that we'll be looking at. And so capital R will be the outside radius of our pipe. And let's look at a small fluid element that we can do some differential equations work on. So in that small little element on the back side, I have some pressure pushing it. On the front side, I have some pressure minus delta loss in front of it. We will call our length of our element just lowercase l. And as I put over here, the radius will be r, and it will have some shear stress pulling back on it. So let's balance out the forces that we have in this element, pushing on this element. So what we do is we have a back pressure. That'll be pressure times pi r squared, little r because we're just looking at the element, and then we're going to integrate that over the whole pipe. And then I have my front pressure, which will be a negative acting the other direction, so minus P minus that pressure loss. And so what we're going to do for that pressure loss, since we are losing pressure as a respect to x direction, we're just going to call that whatever we're losing dp dx. And then we will also multiply that by pi r squared. And now the last thing that we have is we also have the shear stress retarding the motion. So it's going to be the shear stress, and we need to multiply that shear stress, which is a force density, by the area. And so the area of that element will be the circumference, so 2 pi r times the length. And so we want to balance those out and have those all equal 0. So we have a pi and an r in each of these terms. So we'll divide through and get rid of those. I have a plus p times r minus p times r. So that will all drop out. And so I'm just going to be left with the dp dx dp dx r and the shear stress term. So if I take those and separate those out, that'll be a positive dp dx times r is equal to, I'll move the shear stress to the other side, shear stress times 2L. Now, assuming that we have a Newtonian fluid, which most fluids are, we can recall that the shear stress in a Newtonian fluid is negative viscosity times how the x velocity changes with the other direction. When we set it up for Couette flow, we used du dy, but now that we're doing Poiseuille flow, we'll use du dr because we got a circular pipe, and so the radius is the other direction. So what I'm going to do is I'm going to take this, and I'm just going to plug it right in for my shear stress. So we have dp dx times r is equal to negative mu du dr times 2L. Now I want to rearrange this a little bit. Oops. I'm going to rearrange this equation because I want to separate the variables out and then integrate it. I'm going to assume that dp dx is a constant quantity. And so what that's going to give me is we'll isolate out du dr. And then du dr is going to be equal to dp dx, so that's my pressure loss across the system, times r divided by sorry, I just want to see where I want the negative sign on this side. So negative 2 mu L. So if I separate the variables out, du is equal to dp dx r over negative 2 mu L times dr. So now what I want to do is I want to integrate this over the entire pipe. So I'm going to integrate this from 0 to r, and over here from 0 to r. And then I also want to apply some boundary conditions. And so those boundary conditions are, let's think about it. We have the no slip condition, so that tells us that at u of r, my velocity will be 0. And that is because the fluid that's next to a solid object will maintain the same speed as the solid object because there's no slip between the fluid and the solid object. And since the outside of the pipe is not moving, we'll have things set at 0. So what that's going to do is when we plug that in, and we only need one boundary condition because we're only integrating one order of magnitude. So if we integrate that, what we'll end up with is u as a function of r. So my velocity, how it changes in the r direction, is going to be negative dp dx times r squared over 4 mu 1 minus r squared, little r squared over big R squared. So we can find the velocity at any point in our profile in the radial direction using this equation, where I need to know the pressure drop, I need to know the outside diameter of the pipe, or outside radius of the pipe, and I need to know what fluid that I'm dealing with. So what this gives us, this is our velocity profile for a laminar flow. Now the main thing to note is laminar. This is not the velocity profile for anything but a laminar flow, which means that our Reynolds number, based on diameter of the pipe, we're talking less than a 2300 Reynolds number. What's really nice about this equation is we can find out what the velocity is anywhere, so we know exactly what's going on. Now if we want to think about it, let's figure out where our maximum velocity in this pipe would be. So thinking about it, thinking of the equation, this term right here, if we look at it, the biggest that can be is 1, because this is 1 minus something. And so no matter what it is, it's going to be less than 1, except when little r is 0. Little r is 0 is going to be along the center line. So the maximum this velocity can be would be along the center line, which should make a lot of sense, because if we think about the way that entrance length happens before flows fully develop, the center line is the last part of the fluid flow that's inviscid. So there should be the least amount of friction there, so I should expect the fastest speed. Because of that, what I can do is, okay, when this is 0, this term becomes 1, and so then what I'm left with is the maximum velocity that I can have, which is on the center line. So u max is going to be equal to negative dp dx times r squared over 4 mu. There's no point in the velocity field that will be faster than that. Because of that, a lot of times you'll see this equation written as u of r is equal to u max times 1 minus r squared over r squared. Now from that, we can define a couple of key parameters. Once again, though, this is for laminar flow. I can't stress this enough. If you try to use these in turbulent flow, it is not going to work out. So the first thing we need to talk about and define is, okay, we have dp dx. What is dp dx? That's our pressure drop in the x direction. And as we've put together in previous lectures, I know that dp dx is change in pressure divided by our specific weight plus change in height. Now that would be the change in static and hydrostatic pressure divided by L, because that would be our change in length. So dpdx, since we're assuming it is a linear function, all we're really doing is looking at what's the complete change in pressure. We're going to divide that by the complete change in length. And actually, typically, it's a little bit easier to write this as dp plus gamma dz divided by L. That way we can just all have it in one line. And so once we have this, what we can do is we can start plugging things into different equations. Because I know exactly what the velocity is going to be, I can sit there and calculate out, okay, how do I use this to find the average velocity, the shear stress, and the head loss? And we'll take care of that in the next video.